Stephen Hawking and his views on the end of the universe. As one of the first to propose the collapse of the universe, Hawking has bold views on the end of the universe. Are we living in the end of the universe, or is there another theory to explain this end? Stephen Hawking, one of the most renowned theoretical physicists of the 20th and early 21st centuries, spent much of his life contemplating the grandest questions of existence. Among the most profound of these was the fate of the universe itself. What is the ultimate end that awaits the vast cosmos? Will it collapse, rip apart, fade away, or perhaps change in ways we can scarcely imagine? Through decades of research, collaboration, and public engagement, Hawking offered bold and evolving views on these cosmic mysteries, drawing upon the latest developments in physics and cosmology. To understand Hawking's perspective, we must first explore the history of cosmological thought, the scientific breakthroughs that shaped his ideas, and the ongoing quest to decipher the universe's ultimate destiny. To begin, it is essential to consider the backdrop against which Hawking's ideas emerged. The 20th century witnessed a revolution in our understanding of the cosmos. Edwin Hubble's discovery in the 1920s that distant galaxies are receding from us, implying that the universe itself is expanding, transformed the ancient static view of the universe into a dynamic, evolving one. This expansion, first predicted by the equations of general relativity, suggested that the universe had a beginning, the Big Bang. But if the universe had a beginning, might it also have an end? By the mid-20th century, physicists and cosmologists proposed several scenarios for the universe's fate. The Big Crunch was one of the earliest and most compelling. If the density of matter in the universe were high enough, the force of gravity would eventually halt the expansion and reverse it, causing the universe to contract, heat up, and ultimately collapse back into a singularity, a mirror image of the Big Bang, but in reverse. This cosmic collapse would mark a definitive end, a final act in the universe's grand drama. It was against this backdrop that Stephen Hawking entered the scene. In the 1960s and 1970s, Hawking, together with Roger Penrose, developed groundbreaking mathematical theorems about singularities, regions where the known laws of physics break down, such as those at the centers of black holes and at the moment of the Big Bang. Their work demonstrated that under very general conditions, singularities are an inevitable consequence of general relativity. This implied that the universe's beginning, the Big Bang, was indeed a singularity. But what about the end? Early in his career, Hawking was among the physicists who considered the possibility of a closed universe, one with enough matter to eventually halt its expansion and trigger a collapse. In this scenario, the universe would end in a big crunch. The mathematics suggested that the end would be as violent and singular as the beginning, a state of infinite density and temperature, a cosmic finale in which space and time themselves would cease to exist. For a time, this was seen as a plausible outcome, and Hawking's work played a significant role in shaping this view. However, science is not static, and neither were Hawking's ideas. As cosmological observations became more precise, the evidence began to accumulate that the universe might not have enough matter to reverse its expansion. In the late 1990s, a dramatic discovery changed everything. Distant supernovae were observed to be dimmer than expected, indicating not just continued expansion, but an accelerating one. This acceleration was attributed to a mysterious force called dark energy, a form of energy that pervades all of space and drives the universe outward at an ever-increasing rate. With this discovery, the Big Crunch scenario began to lose favor. If dark energy continues to dominate, as current observations suggest, the universe will not collapse, but will expand forever. This led to the consideration of other possible ends: the Big Freeze, in which the universe cools and fades away as it expands, and the Big Rip, in which dark energy eventually tears apart galaxies, stars, planets, and even atomic structure. Hawking, ever responsive to new data, adapted his thinking accordingly. He recognized that, with the discovery of dark energy, the universe's expansion appears destined to continue indefinitely. In public lectures, interviews, and writings, Hawking acknowledged that the Big Crunch was unlikely under current models. Instead, he turned his attention to the implications of an eternally expanding universe. But Hawking was never content to accept simple answers. He delved deeper, exploring the quantum nature of space and time and how these might influence the universe's fate. One of his most famous contributions was his work on black holes, demonstrating that they are not completely black but emit radiation, now known as Hawking radiation, and can eventually evaporate. This insight had profound implications not just for black holes, but for the cosmos itself. If black holes can evaporate, what does this mean for the ultimate future of the universe? In a universe that expands forever, galaxies will drift apart, stars will exhaust their fuel, and black holes, the last remnants of stellar evolution, will gradually radiate away. Over unimaginably long timescales, the universe would become cold, dark, and dilute, a scenario called heat death, or the Big Freeze. In this endgame, the cosmos does not collapse or explode, but simply fades into a thin, cold fog of particles and radiation. Yet Hawking also speculated about even more exotic possibilities. In his later years, he explored the idea that the universe might not be a single, isolated entity, but part of a multiverse, an ensemble of many universes, each with different physical laws and constants. In this context, the end of our universe might not be the end of all existence, but simply one chapter in an infinite cosmic tapestry. Hawking also considered the role of quantum mechanics in the fate of the universe. Quantum effects, he argued, could allow for the spontaneous creation of new universes, even as ours winds down. In this vision, the end of one universe might give rise to another, in an endless cycle of birth and rebirth. Returning to the central question, are we living in the end of the universe? According to Hawking's later views, the answer is nuanced. In the grand scheme of cosmic time, humanity exists in the relatively early stages of the universe's life. The stars are still burning, galaxies are still forming, and life is flourishing on at least one small planet. The universe's ultimate end, whether it be heat death, a big rip, or something even stranger, lies trillions upon trillions of years in the future. But Hawking also warned that, while the universe itself may have a long future, humanity's survival is far less certain. He speculated that we face many existential risks, some of our own making, such as nuclear war or environmental destruction, and others from the cosmos, such as asteroid impacts or gamma-ray bursts. In his later years, Hawking became a passionate advocate for the exploration and colonization of space, arguing that the long-term survival of our species depends on our ability to leave Earth and settle new worlds. In summary, Stephen Hawking's views on the end of the universe evolved dramatically over his lifetime, reflecting the dynamic nature of science itself. He began by exploring the possibility of a collapsing universe, the Big Crunch, but adapted his thinking in light of new evidence pointing toward eternal expansion. He contributed seminal ideas about black holes and quantum effects, which continue to shape our understanding of cosmic destiny. But perhaps the most profound aspect of Hawking's legacy is his insistence on asking the deepest questions and following the evidence wherever it leads. The end of the universe remains one of the greatest mysteries in science. Will it collapse, freeze, rip apart, or transform in ways we cannot yet imagine? The answer remains elusive, but Hawking's work has brought us closer to understanding, and his example inspires future generations to keep seeking. To delve deeper into the scientific details, let us explore the main theoretical possibilities for the end of the universe, the evidence for and against each, and how Hawking's ideas interact with them. The first scenario, the Big Crunch, envisions a universe that expands for a time, then reverses into contraction. The key parameter here is the density of matter and energy. If the density, known as the critical density, is exceeded, gravity will ultimately overcome the expansion. In this view, galaxies would slow, then begin to approach one another, eventually merging into a hot, dense fireball, culminating in a singularity. Hawking's early work on singularities suggested such an end was mathematically plausible, and at the time, cosmologists did not know if the universe's density was sufficient for this outcome. However, measurements of the cosmic microwave background, the afterglow of the Big Bang, helped determine the universe's geometry and density. The stunning revelation in the 1990s that the universe's expansion is accelerating, not slowing, implied that gravity is not winning the cosmic tug-of-war. Instead, a repulsive force, dark energy, dominates. This ruled out the Big Crunch, at least given our current understanding. The second scenario, the Big Freeze or heat death, arises naturally from an ever-expanding universe. As space stretches, galaxies move farther apart. Stars burn their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Over billions and trillions of years, even these remnants fade or evaporate, as Hawking showed. The universe becomes dark, cold, and empty, an abyss where entropy, the measure of disorder, reaches its maximum. In this scenario, time continues, but nothing meaningful happens. The cosmos becomes a wasteland, a shadow of its former self. A third possibility is the Big Rip. Here, dark energy is not constant but increases over time. If this form of phantom energy exists, it could eventually overpower all forces holding matter together. Galaxies would be torn apart, then solar systems, then planets, then atoms themselves. The universe would end not in a whimper, but in a final, catastrophic rending. While current evidence does not favor this scenario, it cannot yet be completely ruled out. Hawking's work, particularly on black hole evaporation, adds a unique twist to these scenarios. He showed that even the most enduring objects, black holes, are not eternal. Over vast timescales, they radiate energy and disappear. Thus, in the far future, the universe will be empty not just of stars and galaxies, but of even the black holes themselves. Only weak radiation and subatomic particles will remain. Yet, the story does not end there. Hawking was deeply interested in the interplay between quantum mechanics and gravity, especially near singularities. He famously proposed that the universe has no boundary in imaginary time, suggesting that asking what happened before the Big Bang might be meaningless. Similarly, the end of the universe might not be a simple singularity, but a quantum event beyond our current grasp. Moreover, Hawking's engagement with the multiverse hypothesis opens the door to even stranger possibilities. In some models, new baby universes could bud off from our own, each with different physical laws. In this context, the end of our universe is not the end, but a transition point, a fork in an infinite cosmic road. Hawking also pondered whether information is truly destroyed in black holes, a question that touches on the fundamental nature of reality. If information is preserved, as quantum mechanics suggests, then perhaps the universe's end is not a total erasure, but a transformation. The final state of the universe could encode everything that ever happened within it, in ways we are only beginning to fathom. Returning to the present, are we living in the end times of the universe? The answer in cosmic terms is a resounding no. The universe is about 13.8 billion years old, but the processes that will govern its ultimate fate, black hole evaporation, proton decay, the dissipation of dark energy, unfold over timescales trillions of times longer than the current age. For humanity, the stakes are different. Our planet, our species, and even our solar system have finite lifespans. The sun will exhaust its fuel in about 5 billion years, long before the universe itself faces its demise. Yet Hawking's perspective was always both cosmic and human. He saw the end of the universe not merely as a scientific puzzle, but as a challenge to our imagination and a call to action. He urged us to cherish our brief moment in the sun, to explore the cosmos, to seek understanding, and to build a future worthy of the universe's grandeur. In the end, Hawking's views on the fate of the universe serve as a bridge between the known and the unknown. His work illuminates the deep links between gravity, quantum mechanics, and cosmology. His willingness to revise his in light of new evidence is a model for all seekers of truth. And his curiosity about the universe's end reminds us that, whatever the final answer, the journey of discovery is its own reward. So, as we gaze into the night sky, we can appreciate that the universe's story is far from over. The stars will shine for eons, the galaxies will dance, and the mysteries will endure. We are not living in the end of the universe, but in a golden age of exploration and wonder, a time when, thanks to visionaries like Stephen Hawking, we can ask the deepest questions and dare to seek their answers.